Hello, welcome to Chemistry Travels. So today we are going to look into an interesting topic, carbohydrates, which is a very simple topic, and we've already dealt with this topic some time ago, where we saw the basics of carbohydrates like its definitions, classification, examples, and so on. So if you've not watched part 1 of this video, please do check out the link in the description box. Watch part 1 and then let's move on to part 2. So in part 2, we are going to deal with the configuration of those various examples of carbohydrates that we saw in part 1. Also, we will see how we can increase or decrease the number of carbon atoms in several carbohydrates, that is chain lengthening and chain shortening of carbohydrates through various organic reactions which we are all very familiar with. Okay. So we saw that carbohydrates are polyhydroxy, aldehydes or ketones. And depending upon the functional group that is present, they can be classified into aldosis or ketosis based on whether aldehyde or ketone is present respectively. Right. And again, this aldosis and ketosis, we saw that based on their number of carbon atoms, like 3 carbon atoms present in the chain, or 4 carbon atoms, 5 or 6 carbon atoms present in the chain, we classify them as tetriose, tetros, pentos, hexos and so on. So it was like aldose group means it will be aldotriose, aldotetros, aldopentos, aldohexos. And similarly for ketose groups, it will be like ketotriose, ketotetros, ketopentos and ketohexos. We saw this already. Now let's try to write the configuration for aldosis. So to start with, we have the aldotriose, right? And in aldotriose, the simplest one is glyceraldehyde. Aldotriose, 3 carbon atoms. So we have a chain like this. There is aldehyde group here, CHO, and at the bottom we have CH2OH. Okay. Now we have H and OH to be attached. 3 carbon atoms are there and we have H and OH to be attached. So I can have H here, OH here. This is one possibility. Another possibility is the same chain, CHO here, CH2OH here, and I can have OH at this side and H on the right side. 2 possibilities are there. So this is the simplest molecule, glyceraldehyde, which is the simplest aldotriose, glyceraldehyde. And if I have H on the right side, it is deglyceraldehyde. Okay. And if I have it on the left side, this is L form of glyceraldehyde. Okay, there is D-glyceraldehyde and there is L-glyceraldehyde, and this, based on this, keeping this as a standard, keeping glyceraldehyde as a standard, we can label D or L form to all other groups of all other upcoming carbohydrates also. How do we do that? So any configuration which has this particular portion, the bottommost portion is of this form, CH2OH, and the next carbon, the second carbon, with H on the left and OH on the right, will always be labeled as D form. Similarly, this is the D form. And similarly, any configuration, irrespective of the number of further adding up of carbon atoms, this bottom portion, CH2OH, with the next carbon having OH on the left and H on the right, this form is the always be the L form for all upcoming carbohydrates as well. Clear? So for further upcoming configurations, let's consider deglyceraldehyde and move on to all other various forms. Let's keep L-glyceraldehyde aside. Okay. So we'll go with this deglyceraldehyde and write the configuration for other carbohydrates. This is our deglyceraldehyde. Now from here, I have to increase the number of carbon atoms. So one more carbon atoms will come. So two possibilities are there when I increase the number of carbon atoms. One is this CH2OH is there as such. This HOH is also there as such. Similarly, one more will be there of the same form, CHO. Now, what is the difference that can come? One more extra carbon atom is added up now, right? So 1, 2, 3, 4. From 3 carbon atoms, we have moved on to 4 carbon atoms. And now, on that extra carbon, one possibility is H coming here on the left and OH coming on the right. Right. Another possibility is OH coming on the left and H coming on the right. Two possibilities, but still they both are D forms because we consider only the bottom portion, H, that HOH, first HOH. That one is on the left, hydrogen is on the left means it's D, hydrogen is on the right means it's L. So in both the cases, first HOH, after CH2OH, the next HOH, H is on the left, so both of them are D forms. And for the next upcoming atom, I can put H either on the left or on the right. So based on that, I got two forms. So from glyceraldehyde, I started with glyceraldehyde. This was my glyceraldehyde. And from there, I got two things. What are those? This is erythrose and this is triose. From glyceraldehyde, I got two things, erythrose and triose. Okay, this is both of them are D form, D-erythrose and D-triose. Okay. Now each of this can be further increased. Erythrose will be further increased in number of carbon atoms. Triose further can be increased in number of carbon atoms, and we'll see what happens. And these are the, we started with aldotriose and now this is the aldotetrose, right? Erythrose and triose are the aldotetrose. Okay. Now we have our erythrose here, we have our triose here. And further, from them, we can add up one more carbon atoms. Here, where we had 4 carbon atoms, we moved on to 5 carbon atoms. Now, erythrose can have two possibilities where one is H being here and OH being on the right. Another possibility is OH being on the left and H being on the right. Two possibilities. Similar goes for the case for triose, where I can have H over here on the left and OH on the right. Or the reverse, OH on the left and H on the right. These are the possibilities. And each of them have a name. From erythrose, we can get ribose and arabinose. This is ribose and this is arabinose. We got ribose, we got arabinose. Similarly, from triose, we get two things. One is xylose and the other one is lysose. Ribose, arabinose, xylose and lysose. Now further, so this was aldotetrose. From there, we got aldopentose. Right. All 5 carbon atoms, all of them, ribose, arabinose, xylose, lysose, all of them are aldopentoses. From here, further if we increase, each of them, riboses will have 2 possibilities of aldohexose, further increasing. Arabinose will have 2 possibilities, xylose and lysose also will have 2 more possibilities of for aldohexoses on increasing the carbon atoms. Okay. Similarly, now if we consider ribose and arabinose alone, this ribose has a possibilities, 2 possibilities, where one is H being on the left, OH, and H being on the right, which 2 possibilities. Similarly, arabinose has 2 possibilities, H being on the left, so OH will come on the right, and H being on the right and OH coming on the left. So, this is known as allose and this is aldose. From ribose we get allose and aldose, whereas from arabinose we will get our glucose, a very important molecule which we will be dealing with this compound glucose further in detail, and with glucose we have mannose. Okay, from ribose and arabinose we got allose, aldose, then arabinose gave glucose and mannose. Okay, then similarly we had two more on the other side, those also we will split to aldohexoses. Okay, similarly we had xylose and lysose that came from the trio side, right? So xylose can be split into two, with when it goes to aldohexose, extra carbon atom would further give rise to two possibilities. Xylose would give rise to gulose. This possibility is gulose and this possibility is idose. Similarly, this lysose can give rise to two possibilities, galactose and talose. Galactose and talose. So the various possibilities are gulose, idose from xylose, and from lysose we have galactose and talose, giving rise to these all being the aldohexose group. Okay, so in a gist we can say that glyceraldehyde, we started with the aldotriose glyceraldehyde, went to aldotetrose, erythrose and triose. From there we went to aldopentoses, which is ribose, arabinose, xylose and lysose, and from there we went to the aldohexoses, which is allose, aldose from ribose, glucose mannose from arabinose, gulose idose from xylose, and galactose talose from lysose. Okay. Similarly, if we consider the case of ketosis, they will have ketonic group. As you can see here, see this ketonic group is there, and now this is the least one, ketotriose with 3 carbon atoms. From there I moved to 4 carbon atoms, putting H and OH, that will give to erythrulose. Then from there again increasing carbon atom would give rise to ribulose or xylulose based on whether it is HOH or it is OHH. Two possibilities. And further this ribulose can give rise to increasing carbon atom based on HOH. We get psychose and fructose. Fructose again similar to glucose, an important molecule that we will be dealing in detail further. And coming to the xylulose side also, similar to how we wrote this aldohexoses and all, we can write here also increase the number of carbon atom and put H and OH in two possible ways, giving rise to sorbose and tagose. Okay. So now that we know the various configuration for the aldoses, ketoses and all, we will look into how we can lengthen the chain or shorten the chain in the number of carbon atoms of carbohydrates. Like what we can do for first thing is lengthening of the chain, that is ascending the sugar series where I am increasing the number of carbon atoms in my carbohydrate chain. And this can be done using a method called the Killiani Fisher synthesis. To explain this, I will take up the simple carbohydrate, simple aldotriose. We will start from glyceraldehyde. Right, okay. So I have my glyceraldehyde, HOH and CH2OH. This is my deglyceraldehyde. This is aldotriose and I want to increase the number of carbon atom in this glyceraldehyde, and from this I am going to form the aldotetrose using the Killiani Fisher synthesis. So for that, the first step is to treat this with hydrogen cyanide or HCN. I treat this with HCN. So when I treat this with HCN, I have a CHO group that can react with hydrogen cyanide, a very basic organic reaction. HCN, aldehydes react with cyanides, forming cyanohydrin, right? So what happens now? HOH, CH2OH, then the CHO will change to CHOH with a CN, right? Cyanohydrin is formed. This extra CHOH and CN. This is what is formed when the CHO reacts with HCN. The remaining bottom portion is there as such. Or there is also one more possibility where the H and OH can be in the reverse direction. That is CN OHH, then the bottom portion SH, HOH and CH2OH. Right. Two possibilities are there. And now let us just consider for the time being this particular one, this HOH, H on the left and OH on the right, and carry forward with this Killiani Fisher synthesis reaction. So if I move forward with this reaction, next what I should do? Now already chain lengthening has happened. An extra carbon CN has been introduced, which means that to the 3 number of carbon atoms, a 4th carbon of CN has been introduced. The chain has already lengthened. Now my aim is to convert this CN back to CHO. That is my aim. So for that, first I treat this with barium hydroxide and H2SO4. Barium hydroxide and H2SO4 treatment of this particular cyanohydrin will convert the CN group to carboxylic acid, COOH group. COOH, remaining everything, this H, OH, OH, everything is there, CH2OH is also there. Now, in the next step, what happens is a water molecule gets eliminated. This from COH, that OH, and from one of the OH, H goes and a gamma lactone or lactonization takes place, giving rise to gamma lactone. This is like water molecule goes off as minus H2O, and what is remaining is CO, H, OH, this is H, this is a gamma lactone that is formed, and the bottom CH2OH is as there as such. See, so a gamma lactone is being formed, and now I have to break this gamma lactone or reduction using sodium amalgam, NaH. Sodium amalgam will cause the reduction of this lactonic part and give rise to aldehyde group, CHO, and this is HOH, and this also will become HOH, and I would have CH2OH at the bottom. And this is my aldotetrose. I started with triose, glyceraldehyde, and I ended up at tetrose. Right. What were the steps involved? First, with HCl, they formed cyanohydrin. From there, with barium hydroxide and H2SO4, COH group came in. Then lactonization came in, giving rise to gamma lactone, which further on reduction gave rise to this is reduction that gave rise to the tetrose. Clear? Now let's look into the chain shortening or decreasing the number of carbon atom or descending the sugar series. So two methods will be discussed in this topic. One is the Ruff's method, Ruff's degradation, or we have the Wohl degradation. So to look into Ruff degradation, let us consider some ketosis, some aldosis. Like for example, I will take aldopendose and move down to aldotetrose. So aldopendose, if I consider CHO, OH, right, 1, 2, 3, 1, 2, 3, 4 and 5. This is an aldopendose. So for Ruff degradation, for reducing the chain length, first thing that I'm going to do is treat this with bromine water. Bromine water. So this bromine water will do a selective oxidation of CHO group alone. And OH groups does not get oxidized, only this aldehyde group gets oxidized to carboxylic acid, COOH. COOH and the remaining portion remains the same. H, 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 then there is OH, OH and OH with CH2OH. Okay, now what I do is, next step is I treat this with calcium salt and also further with Fenton's reagent. What is Fenton's reagent? Fenton's reagent is Fe3 plus in hydrogen peroxide, H2O2 with Fe3 plus ions. It is Fenton's reagent. So what happens is, now the COOH, here what happens is, in presence of calcium salt, this will be COO minus. So let's write it as two steps only, so you'll understand it better. So with calcium salt, this will change to COO minus. Then this HOH is there, HOH. One more HOH is there and CH2OH. And to balance that, we have this calcium 2 plus half of that also. 2 plus ions are also there from the calcium salt. Okay. Now in the next step, what's going to happen is, I'm adding Fenton's reagent, which is H2O2 in Fe3 plus. So here what happens is, this COO will come out as CO2 carbon dioxide. And so already that carbon is gone, so chain has decreased. Now this portion, what will happen to, what happens here is, this gets oxidized to CHO and Fe3 plus gets reduced to Fe2 plus. All this will happen when we add this Fenton's reagent, and finally what we get will be my desired product. CHO, HOH, HOH and CH2OH. I started with aldopentose and came down to aldotetrose. How I came? First I treated with bromine water, which gave rise to selective oxidation of the CHO alone to COOH. Then treatment with calcium salt gave rise to this particular molecule here, compound here. And then further treatment with Fenton's reagent, which is H2O2 and Fe3 plus ions. So this, from the COO minus, that carboxylate part, CO2 has gone out, and the next carbon after that, CHOH, now that one gets oxidized to CHO, and also what happens, Fe3 plus gets reduced to Fe2 plus, and this is the final molecule. The rest remaining portion remains the same, and this is my chain shortened Aldosis. Clear? So now we have the last topic of this video, which is the Wohl's method for descending or decreasing the chain length or descending the sugar series. Wohl's method, here again I considered some, like similar to my Ruff's degradation, I can consider an aldopentose. So I take CHO, HHH, then OH, OH, OH. This I took an aldopentose. So first thing that I do is I have to treat it with hydroxylamine. So when I treat with hydroxylamine, this aldehyde would get converted and would form an oxime. What is being formed? C double bond N OH. Everything else remains the same, and what I got, the CHO got converted to an oxime with hydroxylamine. And now what I have to do is, next I treat this with acetic anhydride. What is acetic anhydride? CH3COO CO CH3. When I do this, the H2O will go out of this minus H2 from this top portion one HOH would go and I would get a cyanide group, CN group there. Instead of that oxime part, now it's a CN group. And in the remaining portions, what happens is all these OH hydroxyl groups will now change to OAC. That acetate group would come in. So it's like H, OAC, H, OAC, H, OAC, and then there is this CH2OAC. So this particular oxime portion became cyanide, and then there is all this every OH changed to OAC with acetic anhydride. And in the last step, to remove off the cyanide and to convert all this OAC back to OH, I am treating this with a very high amount of base. Excess of base, like for example AgOH silver hydroxide. When I treat, what all happens is this CN would go off and this particular group gets oxidized to CHO, and all this also gets converted to OH, OH, OH. Okay, the C and cyanide group, when I treat it with excess base, cyanide group is going off and this HOAC is getting oxidized to aldehyde group, and the remaining every OAC groups gets converted back to OH, and chain shortening takes place because that CN group has gone out, giving rise to the product that I have been looking for, which is CHO. Then this is there, H, OH. This is there, H, OH, and then the bottom CH2OH is there as H. Right. Started with aldopentose and reached aldotetrose. First with hydroxylamine, it gave rise to an oxime, which on treatment with acetic anhydride gave rise to cyanide group. And to remove off that cyanide group, I brought in excess of base or excess of OH minus ions, and that gave rise to the removal of cyanide, oxidation of the next carbon to aldehyde groups, and all OAC changed to OH, giving rise to my aldotetrose. So that is how Wolf method would be acting for descending the sugar series. We learned about Ruff method for descending sugar series, and for increasing the sugar series, we learned the Killiani Fisher synthesis. So I hope you understood this video, you understood the content of this video. So thank you so much. See you with another video.